we start with brief question time. Unfortunately, as of today, I'm actually teaching this course alone because Andreas left us, which is a bit unfortunate, and especially since if you want to ask any questions, there's nobody who's currently following the chat. So in that case, please just unmute yourself and ask the question, and then I will surely hear that. All right. So last week we talked about nonlinear regression techniques, and we have seen that there are two easy approaches to reformulate the classical multivariate linear regression model such that nonlinear relationships between the regressor and the endogenous variable can be formulated in such a way that that the entire model appears as if it is a linear regression model. So we, for instance, can substitute a single regressor variable by powers of that variable, in which case what we get on the right-hand side of the regression equation is a polynomial, which is nonlinear. Or we can substitute either the endogenous variable or the regressor by its logarithm, in which case, again, if we look at the variables themselves, we get a nonlinear relationship. But in either case, the relationship between the regressor on the left-hand side, or the log regressor on the left-hand side, and what is on the right-hand side is formally still a linear relationship. So that's a very tricky and easy way to approach nonlinear problems. Okay, so we have seen that actually the multivariate linear regression model is a good starting point also for nonlinear relationships. And it might be a bit surprising, but if you really understand the statistical issues of the multivariate linear regression model, you are basically excellently equipped with econometric knowledge, and everything else that's coming from now on is either a special case or slight generalization of the multiple linear regression model. All right, so today I'd like to introduce a second approach to, well, kind of nonlinearity, which is called interactions. Again, formally, that's not really new, but the interpretation is interesting, and there's a wide field of applications where you can use these interaction terms. So fundamental good understanding of interactions is really relevant for empirical work, even though formally it's nothing new. Okay? And this is what we will start with today, unless there are any questions, either concerning what we did last week or before, or anything else. Okay, that seems not to be the case. So let me just share the screen. And here we go. So today we are going to talk about interaction terms. What do we mean by interactions? Well, let's have a look at our running example again. We always looked at this example where we tried to explain the test score outcome in various school districts by the average class size in that district. And we have seen, looking at the raw data, that if the class size gets larger, then the test score goes down a bit. Not very much, and there's a lot of variation, but on average, the larger the classes, the smaller the test score. Okay. And if we assume a multivariate linear regression model, multiple linear regression model, then the marginal effect of decreasing or increasing the class size is constant. That's just one of the main properties of a linear regression model. So the marginal effect is just a constant. If you increase the class size by 1 unit, then the effect on the test score will always be the same under the linear regression model. No matter whether the class size is already large or small, or whether we are in a district with high average incomes or low average incomes, or whether we are in a district where many students have to learn English because it's not their native tongue, or whether we are in an area where all the students already speak English as their mother language. So one of the fundamental assumptions of the linear regression model is that the marginal effect is constant. But of course, if we think about the effect of class sizes on learning outcomes, we might assume that decreasing the class size might have different effects under different circumstances. So, for instance, decreasing the class size might not have much of an effect in districts where most students speak English well, but it might be really important for those districts where the students do not speak English as a native language. So that's a conceivable assumption. It might be the case that if we decrease the class size, that is much more effective, meaning it has a higher marginal effect in districts where the share of non-native speakers, the percentage of English learners, is high, because those students need more attention by their teachers than students that speak English better because it's their native language. Okay? So that's a conceivable assumption, but this would not be compatible with the multiple linear regression model, because in the multiple linear regression model, the marginal effect is always and everywhere the same. So if we take into account the possibility that the marginal effect of the class size depends on other circumstances, then the marginal effect, which is written here, so the change in the test score relative to normally unit change in class sizes, then this marginal effect is no longer constant. But it might depend, for instance, on other regressor variables. For instance, in this case, the percentage of English learners, because the marginal effect might be high if the percentage of English learners is high, and the marginal effect might be low if the percentage of English learners is low. Okay, that's just a story, but we could think about causal relationships which work that way. All right, so in a more general notation, going away from this running example to the more general case, we might say that the marginal effect of one regressor variable, say x1, does depend on other regressors, for instance on x2, in which case this term here, the marginal effect, the causal effect, if you like, the effect we are interested in, is no longer constant. So how could we model such interactions? And this is what we call interaction, by the way. So it's the meaning that one regressor or a group of regressors has an impact on the marginal effect of other regressors. So that's where they interact. Okay, and we start with a very easy case where we only have two dummy variables, so 0, 1 variables. Then we go over to the case where we have one dummy variable and one continuous variable. And then last, we consider the case where we have two continuous variables. And then once you understand these cases, then it's easy to generalize that to any multiple linear regression framework. All right, so we start with a case where we have a linear regression, but only two dummy variables on the right-hand side. So the term linear regression is a bit exaggerated in that case, but let's look at that case first, nevertheless. So let's look at the case where we have an interaction between two dummy variables. So both regressors, and there are only two regressors here, both regressors are dummy variables. So the model that we have already encountered before would look like this. So that's the classical case of a multiple linear regression model with two dummy variables. So on the left-hand side, we have the endogenous variable, then we have the intercept beta naught, we have the first slope coefficient d1, and the second slope coefficient for D2. So beta 1 is for D1, first dummy, beta 2 is the slope coefficient for D2, the second dummy variable, and of course the error term. So instead of x1 and x2, as we normally denote them, we write these variables as D1 and D2 just to make it clear that these are dummy variables. So they only take on value 0 or 1. And of course, in this classical framework, that's without interactions, the interpretation is just as we have learned before. So beta 1 is the expected change in y if we switch the first dummy variable from 0 to 1, because if it's 0, then the average of y would be beta 0 plus beta 2 d2 plus ui, and if it's 1, then the difference would be beta 1. So beta 1 is just the expected change in the endogenous variable if we switch from d0 to d1. Okay, we've seen that before. In this model, the change in y, so the marginal effect of d1, does not depend on the value of the other variable. Okay, so if we switch d1 from 0 to 1, then the expected value of y would increase by beta 1, and it does not really matter whether d2, the other dummy variable, is 0 or 1. Okay, so the marginal effect is constant, and there's no interaction in this classical model. So let's add an interaction term. How could we model that? And the answer is surprisingly simple. We simply add another regressor on the right-hand side, which is the product of the two dummy variables. Okay, so the black part here is the one we've seen before, and the red part is the new interaction term. So the term in brackets here, the product of the two variables, that's the interaction variable or the interaction term, and we have a slope coefficient which is attached to this interaction term. All right, so that's adding an interaction term means we add a new regressor, which is the product of two other variables. In this case, of the two other dummy variables. All right, let's look at the effect of this addition. What happens to the interpretation of the marginal effects? Well, let's first assume that the first dummy variable is 0. So we try to find out what is the interpretation of or what is the marginal effect of the first dummy variable. Then, well, here, let's assume first that the first dummy is 0. In that case, the expected value of the endogenous variable is, well, beta 0. This term drops out because beta 1 is 0. Let's assume that the second dummy variable has a certain value, be it 0 or 1. We just call it d2, small d2. So in that case, this term would be beta 2 d2. That's the term here. The interaction term is 0 because we have assumed that d1 is 0. So that drops out. That also drops out. And then the expectation of the error term is 0, given the dummies. So in total, we get beta 0 plus beta 2 d2. That's the expected value for y for those observations where d1 is 0. Now let's look at the case where d1 is 1. So d1 is 1. Oh, I colored that. So d1 is 1. In that case, it doesn't drop out. So what is the expected value of yi? Well, it's the intercept. That's the term here. Then d1 is 1. So this would just be beta 1. That's the term here. Then we have d2 times beta 2. We assume that the variable d2 takes on the value little d2. So we have beta 2 d2. And the intercept could drop out, but it need not. So if d1 is 1, then it depends on the value of d2. Since we just leave that open and call it little d2, we get here beta 3, which is this slope coefficient, times d2. And of course, the expected value of ui is 0. Okay, so this is the expected value of y given d1 is 1. Now let's look at the difference between these two terms. So what is the effect, the expected effect on the endogenous variable y if we switch d1 from 0 to 1? So if we switch from here to here, what is the effect on the expected value of y? But we know what the expected values of y are, namely this one here and this one here. And of course, the change is just the difference between these two terms. So we take the second one and we subtract the first one. And if we do that, beta naught drops out and beta 2 d2 also drops out. But these two terms, beta 1 plus beta 3 d2, they stay. Okay, so the difference between these two is beta 1 plus beta 3 times d2, which means that the marginal effect of a change in the first dummy variable on the endogenous variable is no longer constant. It's not beta 1, but it depends on the value of the other dummy variable, d2. So if d2 is 0, then the marginal effect would be beta 1. The marginal effect of switching the first dummy variable from 0 to 1 would be beta 1. But if d2 is 1, then the marginal effect of d1 on the endogenous variable would be the sum of beta 1 and beta 3. So the marginal effect of d1 depends on the value of d2. Let's look at a numerical example in this case. So this data set is taken from the website of the textbook by Stock and Watson. And we have an example data set which is called college distance, where we have the years of education of students as the endogenous variable, that's ED, education, and we regress that on two dummy variables. The first one is 0, 1, depending on whether the dad has a college education, college degree. If yes, then it's 1. If no, then it's 0. And the second dummy variable is if the mother has a college degree. So also 0 if she doesn't, and 1 if she does. All right, we put that into the LM command. We use the endogenous variable on the left-hand side. Then we have the tilde, which means in this context is explained by. This is as usual, the first variable on the right-hand side plus the second variable on the right-hand side. And now we have to add the interaction term, and that's usually done in R by really adding the product of these two variables. Okay, so you really just use the product sign. And this is the outcome. So that's the estimation. We get the intercept, that's beta naught. We get the first beta, we get beta 1, beta 2, and the slope coefficient for the interaction term, which is negative here. All right, let's put that into a table, or let's put that as a regression equation. Then we can see here that the estimated model looks like this. That's the estimated years of education is 13.5. We add 1.2 years if the dad has a college education. We add 0.9 years if the mom has a college education. And we subtract 0.5 roughly times the product of these two. So if we do compute these estimated years of education for the 4 possible cases, college education for the dad but not for the mom, for the mom but not for the dad, for both or for none, then we get this table here. So if both mom and dad have a college education, then we expect more than 15 years of education. If none has a college education, everything is 0 but the intercept, then of course we have 13.5. And if only one has a college education, then we get these effects here. Okay. So the marginal effect of, say, the dad having a college education depends on the value of the mom's education. So here, it's smaller than here. Here the effect is larger than 1, and here the effect is less than 1. And in the same, and the difference is, of course, the minus 0.48 here. Okay, so the effect of the mom's education or the dad's education on the years of education depends on the spouse's college education level. All right, so that's the case where we have two dummy variables. And if there are any questions, please ask. And currently I cannot actually see the chat. So, okay, it's not the case. So let's continue with case 2, the interaction of dummy variables and a continuous variable. So we have one dummy variable and one continuous variable. Well, the classical model would be this one here. So that's the case without interactions. Intercept, the continuous variable, the dummy variable, and the error term. And of course, this is just a classical linear regression model. This is what we have worked with all the time. There's nothing new. The only change here, well, change, is that we denote one of the variables by d rather than x. So that's the only change here. And of course, if this is the classical linear regression case, then the marginal effect beta 1, the marginal effect of x on y, does not depend on anything. In particular, it does not depend on the dummy variable, because in the linear regression model, in the multiple linear regression model, the marginal effect is constant. It does not depend on anything. Okay, so the marginal effect does not depend on the dummy variable here. If we want to introduce dependence, we have to introduce an interaction term. And the interaction term in this case is added again by adding a new regressor on the right-hand side, which is just the product of the two variables. So there's nothing new. The only difference to the first case is that the notation of one of the variables. And of course, that it's a continuous rather than a dummy variable. So x1 is the only change here. Xi is the only change here. Okay, so the red part is the new interaction term. So an interaction term is just a product of the variables that we want to interact. All right, let's look at the marginal effects here. So what would be, what would happen in this case? Well, let's look at the general model again. So that's just a repetition of the formula we have just seen. First regressor, second regressor, interaction term, and error term, of course. Now we want to find out about the effect of x on y. And to do that, we look at two different cases for the other variable, the dummy variable. Let's first assume that the dummy variable is 0. In that case, this term here drops out because d is 0. And this term here also drops out because d is 0. So what remains is just the intercept plus beta 1 xi, and of course the error term. So that's this formula here. So this is the regression equation between y and x for those observations where the dummy variable is 0, but only for those. Okay. What happens if we switch d1 to 1? Oops, sorry. If we switch d1 to 1, well, in that case, d1 is obviously 1. So in the upper equation here, the d1, well, need not be written explicitly. It's multiplied to beta 2. We can then merge the beta 2, which is just a constant, to the intercept term, which is also just a constant. So we get beta naught plus beta 2. down here, d is 1. So this is just beta 3 times xi. We can merge that with beta 1 xi, and that would give us beta 1 plus beta 3 xi, and the error term. Okay. Now let's look at this regression equation. That's also just a linear regression equation. Actually, it's a simple linear regression equation between y and x. We have an intercept, which is not beta naught now, but beta naught plus beta 2. And we have a slope coefficient, which is not beta 1, but beta 1 plus beta 3. Okay. So in the group where the dummy variable is 0, the intercept is beta naught, and the slope is beta 1. In the group where the dummy variable is 1, the intercept is the sum of beta naught and beta 2, and the slope coefficient is the sum of beta 1 and beta 3. Okay. So what we have, in effect, are two separate regression lines. One regression line for the group of observations where the dummy is 0, the d equal to 0 group, and one different regression equation for the group where d is 1. Okay. And since beta 2 could be any value, and beta 3 could be any value, positive or negative, these are really two separate regression lines. So potential regression lines could look like this. We might have the case where the slope coefficient is actually the same, but the intercept is different. So in that case, both have the same slope coefficient, beta 1, but the intercept would be different. We could have the case where the two regression lines are completely different. They could intersect, but they need not. It could look anyway. One might be steep, one might be less steep, like here. One might have a high intercept term, the other a low intercept term, like here. But it could be anything. Okay? And here we have the case that we have seen on the previous slide, two really separate regression equations. Or we might have the case where the intercept is the same, but the slope coefficients differ. All right. So what would be the marginal effect of x on y? Well, we have seen how to compute that last week. We can compute that by looking at the regression equation before the change, ignoring the error term for a moment, and then looking at the regression equation after the change, and then rewrite that such that the change is on the left-hand side, or we get the marginal effect on the left-hand side. So before the change, that's easy. After the change, of course, the axis changed to x plus delta x, and that has two places where that has an impact. First is here, and of course, the second is here at the end. Okay, and on the left-hand side, that induces a change in y to y plus delta y. Now we subtract the first equation before the change from the second equation, which is after the change. So we compute after the change minus before the change, then beta 0 drops out, it just cancels. Beta 1 x1 cancels. Beta 1 delta x does not cancel, so that remains. And on the left-hand side, only obviously delta y remains. Then we have the beta 2 that cancels. And we have beta 3 times dx that also cancels. And we have beta 3 times d times delta x that does not cancel, and that remains. So this would be the change, or the expected change in y. And if we divide both sides by delta x1, or there's an x1, that's the one missing. Here it's also missing. No, it's not missing. This is too much. So just delete this one, please. We only have one x here, so we don't need the x1. So it's, we just divide both sides by x1, delta x, sorry. Then what we get is the marginal effect of x on y, and that is beta 1 plus beta 3 times d. So the marginal effect depends on the value of the dummy variable. It's not constant, and therefore it's, in a way, it's a linear, non-linear interaction term. Okay, let's look at one example. We use the Californian school data set again, and we define a dummy variable. And the dummy variable is called high English learners, high EL. It's 1 if the percentage of English learners is larger than 10%, and it's 0 if it's less. Okay, so it's kind of coarse variable that tells us whether the students are disadvantaged in a certain way because English is not their native tongue. Then it's 1, and if it's 0, the students probably, or there are only few students that don't speak English as a native tongue. All right, so we just set up the usual regression equation. We have the test score on the left-hand side. We have the class size, our dummy variable, and the interaction term on the right-hand side. We can regress that using the usual commands in R. And you can really just add the product of the two variables as the interaction term. And then this is the estimated outcome that we get from our R command. That's the intercept term. That's the slope coefficient for class size, slope coefficient for the dummy variable, and for the interaction term. Please be careful. The marginal effect of the class size is now not minus 0.97, because that would imply that the marginal effect is constant, and that would mean that if you increase the class size by 1 unit, then the test score would go down by 0.97 units. But that's not the case here, because if you increase the class size by 1 unit, you would also increase this term here by 1 unit. And of course, the total effect on the test score would then depend on whether this one here is 0 or 1. Okay, so that's really important here. A bit like last week. Last week in the polynomial regressions, the slope coefficients were not the marginal effects, because you just cannot increase one regressor by 1 unit, keeping the other ones constant if the other ones are just powers of the first variable. Okay. So in that case, finding the marginal effect is more complex. All right, so possibly interesting hypotheses in this case are that the intercepts for both groups are the same, for the group without a high percentage of English learners and the group with many English learners. Or we might test the regression, the hypothesis that both regression lines have the same slope coefficient, which would mean that the marginal effect is the same in both groups. Or we could even test whether both regression lines are completely identical. So if they are completely identical, that would mean that the percentage of English learners has no effect at all. If they have the same slope, that would mean the marginal effect of class size would be the same in both groups, but one group might have a higher level than the other group. And if the intercepts are the same, then the marginal effects would be different again. So let's test one of these examples. And let's look how we could do that using the linear hypothesis command. Well, first, we simply run the regression using the LM command. And we have the usual formula here. So the test score on the left-hand side, the first variable class size on the right-hand side, plus the second variable, that's the dummy variable, plus the interaction term. This is the outcome of that regression is saved as the rec_r object. We use that as the first argument in our linear hypothesis command. Then we have the hypothesis. In this case, the hypothesis is that the two regression lines are actually the same, which means that neither the intercept nor the slope coefficient is affected. So both have 0. So in this case, it would mean here that beta 2 is 0 and beta 3 is 0. And as usual, we add this part here to make sure that heteroscedasticity is not a problem. We do that all the time. All right, so this is an abbreviation of the outcome of the command. We get an F statistic, which is almost 90. Remember, the F statistic can be used to tell whether the joint hypothesis should be rejected or not. And in this case, the p-value is almost 0. So we do reject this hypothesis, and we have established strong statistical evidence that the two regression lines are not identical. Okay, so whether there are many or few English learners does have an impact on the relationship between class size and learning outcome. All right, that's the second case. Case 3, that's the case with two continuous variables. So it's the same model again. This is really the classical case. We want to see whether the effect of x1 on y might depend on x2. Of course, here it does not, because that's the standard multiple linear regression model with constant marginal effects. But we could add an interaction term. We do that as before. So we just add the product of the two variables as a new regressor on the right-hand side. That's the interaction term. And we now compute the effect of a change in x1 on the endogenous variable. And we do that in the same way as before. So let's look at the relationship between the regressors x1 and x2 before the change in x1. Well, that's just the equation we've written down here. We drop the error term to make it easier to read. Then what happens after the change in x1, keeping x2 constant? Well, x1 is changed to x1 plus delta x1. That happens here and here. And on the left-hand side, that has an effect on y, because y changes to y plus delta y. Then we look at the difference between these two equations. We subtract the case before the change from the situation after the change. So we subtract the first line from the second line. On the left-hand side, what remains is just delta y here. On the right-hand side, the beta 0 drops out. Beta 1 x1 drops out. Beta 1 delta x1 does not drop out. So that's denoted here. Then we have beta 2 x2 that drops out. We have beta 3 x1 x2 that drops out. And we have beta 3 delta x1 x2 that does not drop out, and it's written here. So beta 3 delta x1 x2. If we divide the left and right hand side by delta x1, we get the marginal effect of a change in x1 on the endogenous variable y. And we can see here that this marginal effect is not constant, but depends on the value of the second regressor. Okay? So whether or not x1 has a large or small effect on y can depend on x2. If beta 3 is not 0, which means there is an interaction term, then the marginal effect on one of the regressors depends on the other regressor. Of course, we could do exactly the same thing with delta x2. Then we would get an expression for the marginal effect of x2 on y. And we would see that then on the right-hand side, we would get x1 as an influence on the marginal effect. So the marginal effect of x1 depends on x2, but also the marginal effect of x2 depends on x1. Let's do that for the school data set. So we have an estimation with class size on the right-hand side, the percentage of English learners as a continuous variable, not the more coarse version with high or low. So here's really the percentage as a continuous variable and an interaction term. This is what we get as an outcome from the LM command: intercept, first slope coefficient, second slope coefficient, and the interaction term. So the marginal effect of class size on the test score now depends on the percentage of English learners. And if we just use the formula we derived on the previous slide, we can see that here we have the beta 1 minus 1.12, but then we also have the interaction term here. Okay, so the larger the percentage of English learners, the higher this term here. If the percentage of English learners is 100, then we would get 0.12 here, not 0.0012. So it would be 0.1. And then this term here would be higher. So the effect would be smaller. While if the percentage of English learners is 0, then the marginal effect would in fact be minus 1.12. So there's an impact on the percentage of English learners on the marginal effect of class sizes. So whether we have a high or small effect of increasing or decreasing the class size depends on the situation. If the percentage of English learners is high, this marginal effect would be different. The causal effect would be different from the situation where the percentage of English learners is small. All right, so let's summarize that. We have seen last week and today that nonlinearities can be modeled by linear regression models. We could use polynomials, we could use logarithms, but we can also find out how to get non-constant marginal effects if we use interaction terms. In all three cases, polynomial regression, log regressions, and interaction terms, the estimation is just standard. We use the usual LM command. And also testing is just standard. We just do that as we have done in the usual linear regression model. So there's, in a certain way, there's nothing new. So from the technical side, it's nothing new. It's just the interpretation and the modeling which is new here. So the difficult or the dangerous part here is that the interpretation of the coefficients is different now. In the linear regression model, the slope coefficient is an estimation for the causal effect. And it's just constant. That's very easy. But if you have nonlinearities or interactions, which are in a way case of nonlinearity. So if you have nonlinearities, then the interpretation of the coefficients is different because you can no longer change one of the variables on the right-hand side, keeping everything else constant. And that's the case because if you change one, you will induce changes in other places as well. So in that case, the interpretation of the coefficients is different and you have to take that into account. All right, are there any questions? Then I suggest we make our active study break here. Might take a few seconds until I start the video, but I will see you then back in 5 or 10 minutes or so. All right, see you in a minute.
Hallo, schön, dass ihr dabei seid. Ich bin Leon. Ich mache mit. schön, dass ihr dabei seid. Ich bin Leon. Ich mache mit euch heute die Study Break und
What we have seen so far is that the multiple linear regression model will give us an estimate of the causal effect of some regressor variable X on some endogenous variable Y. So we are normally interested in these causal effects in economics because, and this is the case in, well, proper economics, but also in business, because that's the causal effect is what is relevant for policy evaluation or for policy planning. If we know the causal effect, that means we know what would happen, at least on average, if we fiddle around with one of the regressor variables. So what would happen if we, say, increase the price? Or what would happen if we implement a new labor market policy or a new regional policy? So this question, what would happen if we implemented some kind of policy or some kind of regime or rule, is obviously interesting and very important for policy planning. So that's what we're interested in. And the multiple linear regression model will give us an estimate of these causal effects. But we've also seen that sometimes this estimate is wrong. So for instance, in the simple linear regression model, if we compute the marginal effect of X on Y, but if there are omitted relevant variables, then the causal effect is misestimated. It could be too large, it could be too small, anything could happen, but in general, what we get is just nonsense. We've also seen that if we include these omitted variables, these confounding factors in the multiple linear regression model, then the problem of omitted variables is, well, solved. But that's only the case if we include all omitted variables. So then there must not remain any omitted variable. And last week and today, we have seen that the linear regression model can also capture non-linearity relationships between X and Y. But still, these OLS estimations can go wrong, and the estimators can be biased, and they can even be inconsistent. Biased means they are, on average, or an expectation, larger or smaller than the true effect. Inconsistent means that even if we have a very, very large sample, the estimators, which normally get better and better and better the more information we have, do not get better because the estimation is inconsistent. So getting more information would not help in that situation in finding a better estimator. Right, so the question now, of course, is in which situations are these OLS regressions or estimations valid? So how can we assess the value of econometric studies? And to get more structure into this question, because it's obviously a complex question and it depends on the particular case and so on, but to get somewhat more structure into this problem, how to assess econometric studies, we differentiate between two kinds of validity. We call the first the internal validity. So that means the statistical inference that we are doing, testing confidence intervals and so on, about the causal effect, do hold for the population we study, for the population under investigation. Okay? So it's internally valid in that case. And we contrast that with the external validity, which means that we can generalize what we have found for the population under investigation to other populations. And this could mean under different institutional settings, it could mean for other countries, it could mean for other years or times, or under different policy regimes, or whatever. Okay? So we distinguish this internal validity from the external validity, and one means that it's, well, internally valid means that we did not do anything wrong, and the statistical inference is true for the population we investigate. The more interesting part is, of course, the external validity, and that means that we can generalize what we have found for the population under investigation to other populations. So for instance, if we find that, say, Sweden has a particular successful corona policy, can this be transferred to other countries like, say, Germany or Italy? The external validity is, well, not really more difficult, but it has less to do with methodological questions. So external validity is reasoning about whether or not this generalization from the studied population to other populations is possible or not. That's nothing which is really methodological. So it's more a substantial question. And if you want to answer that question, you really have to know what you are talking about. So you have to know the substantive issue which is relevant in that case. So it's nothing, it's not a statistical question, it's an economic question, which is why we teach methodology to economists. So otherwise you could also just hire a statistician to do the econometric work for you, but that doesn't work because the statistician doesn't know the economic implications and he doesn't know whether external validity is given or not, for instance. All right, so if we go back to our running example, we might ask, can we generalize what we have found out about the relationship between class size and learning outcome? Can we generalize that to other populations? Remember, the running example, we started that many weeks ago, is a data set which was collected in 1999 in California. And of course, we might ask, can we generalize that finding to California in 2020 or 2021? So today, is what we have found out for 1999 still valid more than 20 years later? And of course, many things have changed in these 20 years. In particular, the internet and the availability of say, video teaching material for students has changed dramatically over these 20 years. So it might be the case that back in 1999, class size had an effect on the learning outcome, but today it's no more there. Or it might be the case that the relationship or the effect of class size on learning outcome was small in 1999, but today it's much larger. So since the situation in California has changed over these 20 years, it's not clear that the results we found out about the impact of class size are still valid today. And of course, if we go from California to another state in the United States, say Massachusetts, then again, the institutional settings in the educational policy in Massachusetts is probably different from California. Actually, I don't know because I haven't worked on education policy in America. But if you want to talk about the external validity, then you really have to find out about the institutional settings in California in 1999 and say Massachusetts today. And if we go to other countries, say neighboring Mexico, then the question is also, can we generalize what we found out for California to other countries like Mexico, which have a completely different political situation, which have a different level of income, different level of education, and so on. And of course, even if you could generalize that to Mexico as a neighboring country, the question is, could you generalize that to, say, I don't know, Rwanda in Africa or Vietnam in Asia? So to answer these questions about the external validity, obviously you have to know the institutional setting and you have to know what you're talking about. This is not a statistical question. All right, and the same is true, of course, if you want to generalize what you found out to other institutional settings, say you want to know something about special schools for disabled students, Förderschulen in Germany. Maybe the effect of smaller classes is much different in such schools from say, normal schools in California in 1999. And also bilingual teaching might have an impact on the marginal effect of class size, because if the students do not speak one of these languages as a native language, they might need more assistance in that case, which can only be given or better be given by additional staff. And also we might ask, is what we found out about teaching for students also relevant if we want to educate teachers? Say, on the next higher level, is class size a relevant issue in that case as well? So you see, all these questions are obviously relevant for policy questions, of policy planning, but answering these questions has nothing to do with statistics or econometrics. Answering these questions is really an economic or educational economics question in this case. Right, which is why we won't talk about external validity from now on. Okay? But thinking about this distinction between internal and external validity is very helpful if you want to assess other people's econometric studies. And also, if you do an econometric study on your own, then thinking about these internal and external validity is quite helpful. So just keep that in mind. It's a very helpful tool for thinking about econometric studies. Okay, so if we don't talk much about external validity, because it's not methodological, we will talk much more about internal validity. And actually, everything that we do in this semester is about internal validity. So there are important causes of threats to internal validity. So one we have already encountered, the omitted variable bias. If there's a confounding factor, an omitted variable, which is relevant for the endogenous variable and which is correlated with the exogenous or one exogenous regressor, then omitting this variable will cause the slope coefficients and the intercept coefficient to be inconsistent. Okay? So in that case, the omitted variable bias will give you an outcome where you might think that that is the causal effect, but in reality, it's not. So what you get is wrong. And of course, that's a severe problem for policy planning. If you put more resources into hiring teachers and the effect is much smaller than you expected, that's of course a severe problem. Okay, we've already encountered that. I will talk about it a bit more later on. Misspecified models, we have also talked about that last week. So if you think that the relationship between the regressors and the endogenous variable is linear, but in reality it's not, then you think that you found out a constant marginal effect, but in reality this marginal effect is not constant. So the constant value is wrong, at least for some parts of the distribution. And therefore, again, you make an error if you found your policy planning on such a finding. Okay, so misspecification is also a severe problem. So the incorrect functional form. We did talk about what you can do about that. So we did talk about nonlinear regression techniques like polynomial regression, log models, log-log models, and so on, and interaction terms. We did not talk about formal tests of misspecification. That's a bit more advanced. There are formal tests, but we don't deal with them. And as usual, I'd like to invite you to specialize more in econometrics. It's really an interesting field, and there's much more to learn and really important techniques which are quite useful for empirical work. Another problem which might be a threat to internal validity is the so-called error in variables problem, which happens if you measure your regressors with an error. It's not a problem if the y variable is measured with errors, but it is a problem, surprisingly in a way, that an error in the measurement of the regressors will cause the internal validity to break down. And sampling bias is also a problem. I'll talk about that later. And a very severe problem is the endogeneity problem. And we will also talk more or less for the rest of this term about endogeneity issues and what you can do about that. Excuse me. So let's talk about each of these 5 problems in turn. Some of them we've already seen, so that will be fast. For some of them, I need somewhat more time. So the omitted variable bias, we've already seen that. It occurs if there's a confounding factor, an omitted variable, with 2 properties. The first one is the omitted variable does have an effect on the dependent variable. So it's omitted, but it would cause an effect on the y variable. And second, it's also correlated with at least one of the regressors. Okay? And if that's the case, then what we get is a biased estimation and also an inconsistent estimation and wrong inference, and everything about the causal inference breaks down in that case. So the tests we do are wrong, the confidence intervals we compute are wrong, and, well, in short, the problem is really severe. But also, it's very hard to detect. There's hardly a statistical way to tell whether omitted variable bias might be a problem or not. Okay, so if I give you the result of a regression estimation, and if you do not know anything about the whereabouts, then it's really hard for you to say whether omitted variable bias might be a problem or not. Because just looking at the statistical outcome, the computer outcome, you won't see the problem. So what you need is thinking about the problem, and you need economic theory to say whether omitted variables might be that, well, might not be there in a way. Okay? So it's not enough to look at the output of the computer. The problem is not visible there. What you have to do is you have to think about the problem. You have to reason why omitted variables are not a problem or might not be a problem, or why they might be a problem. Okay, so again, this is not really a methodological question. This is about economic theory. All right, once you realize that there might be important variables which are omitted from your regression estimation, the obvious approach is to look whether you can find data about that variable. And if so, then you just add the omitted variable to the model. But very often it's really hard to find such data. For instance, if you want to find out about the relationship between the length of education, or whether students attend a university or not, and their earnings later on, then an obvious variable that also depends, that also impacts on earnings is the ability of students. So if you're just a stupid guy, then your earnings will be probably lower than if you're really smart. But if you're really smart, you're more likely to go to university. So if you only look at whether workers attended university or not, you will find that a higher education will, on average, induce higher earnings, but that could also be just because the smart people go to university and they would get high earnings anyway, even if they had some other kind of education. So in that case, finding a variable which is a proxy for the ability of the workers or the students is really hard. Usually you won't have data sets where such data are available. Another way, well, that's a bit theoretical, of course, you could try to run a randomized controlled experiment. That's the gold standard in a way. But we've seen in the very first week that running a controlled experiment is usually not really an option in economics. And 2 techniques which we will talk about later on. You could use panel data, Remember, panel data means that you observe the same individuals or the same units period after period. So not only once, as in a cross-section, but multiple times. Or you could use instrumental variable estimation. And we will talk about that in detail later on. So that's the omitted variable problem. It's really severe. It's hard to detect. You have to think about that. You have to reason why or why not it might be a problem. You have to know the economic question you're talking about. And if you want to do something about that, then panel data or instrumental variable techniques might help. We will talk about those techniques the rest of the term. The second problem was the misspecification problem. And this problem occurs when the functional form you assume is not the correct functional form. For instance, you assume a linear relationship, but in reality, the relationship is quadratic, or there's a logarithmic relationship between y and x. In that case, if you assume linearity, you get a constant marginal effect, but in reality, the marginal effect is not constant. So you should not base your policy planning on the estimated constant marginal effect, because that's wrong. And therefore, misspecification is also a problem. We have seen how to approach this problem. You could transform the data. You could look at the logarithms of the endogenous and or exogenous variables. You could do a polynomial regression. So don't include just x, but also x squared, x cubed, and so on. Or you could use interaction terms. The third problem is what's called the errors in variables problem. So far, we have assumed that the regressors are measured without any error. So we actually know the value of xi for each observation. If this is not true, so if the measurement has some kind of error, then the estimation might break down. And of course, there are many sources of measurement errors for the regressor variables. So for instance, recording errors. If you do a survey, then you send the survey employees, you send them to the different households, and they have to ask the question to each household member, say, or each firm or whatever, and they have to type the answer into their computer. Or formerly, they had to write down the answer into the answer book. And of course, an error might happen there. So you might type the wrong answer, you might miswrite something. So that would be called a recording error. Common recording error is that the decimal is placed at the wrong position. So instead of 100, you write 1000 or 10 or whatever. Okay, so that's a trivial error, but it might happen, and it actually does happen. It happens more often than you might think. The second source of measurement error would be what's called the recollection error. You might be interested in the effect of tenure on earnings. So how much more earn workers when they are employed longer in the same firm. And to find out about the effect of tenure on earnings, you could just ask a group of workers, how long have you been employed in a certain firm? So you ask them, since when are you employed here? Or have you been employed here? And then they answer some number, some year, but of course that might be wrong. So if you think back, when were you, I don't know, when happened whatever to you, if that's 5, 6, 7 years ago, you might just give the wrong answer. It's 5 years ago, but you answered 3 years or 7 years or whatever. And that's called the recollection error. People might have the exact information, but they had to look them up, and that's too complicated. So they just answer something which is roughly true, which is nice, but of course, there are kind of recollection errors in that case. Third source of measurement error are unclear definitions. So I might ask somebody, what was your income 2 years ago? And even if they know about their income 2 years ago and they can recollect that, the definition of income is by no way clear. So is it gross income or net income? What happens with social security contributions? Are they part of it or not? What happens with your rent? Is it part of your income or should you subtract that? So there are many, many questions concerning the details of the income definition. And of course, the main distinction between gross and net income is relevant here as well. So if the question is not clearly defined, then of course, different people answering to that question will understand the question differently and therefore will give, in a way, wrong answers. So that's also a source of measurement error. And finally, they could answer in a wrong way intentionally. So if you ask them whether they committed a certain crime, they are probably unwilling to answer correctly and truthfully. So in that case, for instance, if you ask how much tax did you evade 2 years ago, then most people will probably answer none, even if they did. So, and that's also kind of misreporting. So in that case, you get errors in variables. Why is that a problem? Well, let's look at 2 slides here. The problem is that a measurement error in the regressors will yield inconsistent estimators. And we can illustrate that quite nicely if we look at a very simple case, simple linear regression model. We have y on the left-hand side, x on the right-hand side. And we assume that this is actually the true model. And we assume that our assumption number 1 is satisfied. So given xi, the expected value of the error term is 0. So x is the true value, but it's measured with an error. So we do not actually know the true value. What we measure is x tilde. That's the measured value of x. Then we can rewrite this equation here in this way. We add beta 1 times the measured value, and we subtract beta 1 times the measured value. And we rewrite that in this way and say that we have yi as a linear function of the measured value of x plus, and we merge the entire rest into the error term u tilde. So that's the error term, including the effect of the measurement error. The term in brackets here, that's the measurement error. It's the difference between the true and the measured value. And now we compute, or we derive, the covariance between the measured value and the error term, the redefined error term. So that would be the equation that we actually estimate if we work with the measured x values, not with the true x values. If we did that, we can compute the covariance between the measured x values and the error term. We rewrite the error term in terms of the measurement error and the true error term. Then we use the rules for covariances. So we get out the beta 1 here. We cut into 2 this covariances at the plus sign. So first covariance here and then the covariance for the rest. And then we use, again, the rules for the covariances. And we find out, doesn't really matter how this expression looks like, we find out that it's not 0. Okay, so there's correlation between the measured values of x and the error terms. So for the estimated model, our assumption number 1 does not hold, even though it does hold for the true model. So for the measured model, the assumption number 1 is violated, and therefore beta 1 is not a consistent estimator. Beta 1 hat is not a consistent estimator for the true slope coefficient beta 1. All right, so in this case, The estimators are inconsistent, so the problem does not go away if you increase the sample size. The estimators are biased, so on average you get too large, or depending on the parameters, too small values. And it's really a severe problem. And of course, many variables are estimated with measurement errors. So what are possible approaches to deal with this problem? Well, better data, obviously. You could try to model the measurement error. So that's kind of modeling what's actually happening there. Or again, instrumental variable estimation. So we've talked now, I'm running out of time, I just realized. We've talked now about 3 potential threats to internal validity: omitted variables, omitted variable bias, misspecification, and the error in variables problem. I will talk about the other 2 problems next week. Are there any questions? That's not the case. So enjoy the rest of your week, and I'm looking forward to seeing you again next week. Bye-bye.